Okay, we're now going to talk about light intensity. And this is a concept that is fairly easy to understand, but there are many terms that are being used that are very similar, and it could be hard to differentiate what is the difference here. And I believe that many of you are already familiar with, for example, the PPFD and the PFD and the PPF. And you can hear that, yeah, these are being a lot of P's and F's and D's tossed around, and it could be a little bit hard to separate them. But I believe that if I'm going to walk you through them all at the same time here now, it's easier to map them out and see what the differences are. But let's start at the conceptual level, and that would be the light intensity, which is something that I like to think of as the same way as I think about the intensity of a rainfall. So, but instead of water drops falling, we now have photons falling, and the intensity is essentially how many photons are there at a certain time. The problem with this is that there are so many photons in light. The numbers are so tremendously large. So, for example, a typical light intensity in a greenhouse would be 602 million billions of photons for a square meter every second. And it's of course very inconvenient to talk about such large numbers. So therefore we bring in the concepts of the mole and the micromole. Essentially a mole is just a 6 followed by 23 zeros. So instead of saying these huge numbers, we can say, for example, like 6 moles or so forth. And there will be a 6 follow. I mean, it's a way of managing these extremely large numbers without having to spell out all the zeros, so to say. And the micro actually translates into 1/1,000,000th. So a micromole is 1/1,000,000th of a mole. So again, it's a way of managing large numbers. I'm now going to look at light intensity in 2 different perspectives. And the first perspective would be when we talk about the light intensity on a surface. And here we have the PPFD and the PFD as the 2 terms that are being used, the 2 concepts. The PPFD stands for photosynthetic photon flux density, and the PFD stands for photon flux density. So photosynthetic, it means that it's par. Photon, we're talking about photons. Flux, it's a flow. And the density is singling out or indicating that we talk about over an area. So we see in the figure here, we see such an area. We see a square meter, 1 by 1 meter surface, and the light intensity on that surface would be how many photons are hitting that surface on one square meter, and how many photons are hitting that every second. And of course, this is a very large number. But instead of saying 602 million billions, we can just say 1,000 micromoles per square meter per second. So the unit here is the micromole per square meter per second. It's essentially just a large number of photons per square meter per second. So what is actually the difference between the PPFD and the PFD? That's the first P there is removed, and the difference is essentially that when we talk about PPFD, we are only counting par photons, so blue, green, and red photons essentially. PPFD only measures photons with wavelengths between 400 and 700, whereas the PFD is measuring from typically 350 to 750 nanometers. So that means that we are including the UV and the far red as well. I think that the industry standard still is talking often about PPFD, so only measuring par light. But we know that the UV is of importance to the plants. We also know that the far red is of importance to plants. So if you are measuring your light, I would encourage you to preferably measure both, but measuring the PFD, where you include the UV and the far red, is reasonable, because that is light that is of interest to the plants. And if you have, for example, an LED fixture where you have far red LEDs in the fixture, you should of course measure that light, because it has been put there for a reason. It's in that it is in that spectrum for a reason, and that's because it's used by the plants. So that would be the difference between PPFD and PFD. And here we are talking about the light intensity on a surface. But you can switch the perspective a little bit and talk about the light intensity that comes out of a fixture, so the fixture output. And then we see the terms PPF or PF. So we have get rid of the D here. We have no area anymore, but we still have a photon flux or a photosynthetic photon flux. We have flow of photons out of the fixture. And that's the PPF and PPFD, number of output photons every second. And the unit here is then micromoles per second. If you hang such a fixture over a surface, there will of course be a resulting light intensity on that surface. And then we're back on the previous slide talking about micromoles per square meter per second. But that is of course dependent on how high you hang the fixture and what angles the fixture is spreading its light out. So only looking at what the fixture output is not really relevant to the plants. You also have to consider how the fixture is hung with respect to the plant. But still, it's interesting to know how much light is a fixture outputting. And you do that by looking at the PPF or the PF. And again, the difference between these two, PPF and PF, is the same as before, that the PPF, when we have two P's, then we are counting par only. But when we have PF, only PF, then we are including also the UV and the far red. So be aware which one you are using, and I would encourage you to not be afraid to use include the UV and the far red, especially if you are looking at the fixture that has on purpose put such photons in the output, so to say, because if they are relevant to plants. Next up, we're going to talk about efficacy, and efficacy is a way of quantifying how energy efficient a fixture is or a lamp is at converting input energy, electricity, into output photons. And the efficacy is calculated as how many photons do you get out for every input energy. And the unit here is the micromole per joule. So how many micromoles of photons do you get out for every joule that you put in? If you're interested in the math behind this unit, I'm just going to have a quick pop-up here. The output photons is measured, as we know now, in micromoles per second, and the input electricity is typically, or input power is typically measured in watts, and a watt can be rewritten as a joule per second, and then the second seconds are canceling out, and you are left with a micromole per joule. But let's not get stuck in the math and physics here. The unit for efficacy is micromoles per joule. And again, we have the same thing as we have before. We measure efficacy, we denote that typically with PPE or PE. So that's very similar to what we have seen with the PPFD and the PFD, for example. And again, we have, if you talk about efficacy in terms of PPE, then you're only counting the par photons in the output. But again, if you have far red and UV in the output, it could be of interest to also see, okay, how energy efficient is the lamp of producing UV and par and far red, and then you should instead look at the PE. You should include the UV and the far red to quantify how energy efficient the fixture is. Okay, let's move on. Let's talk about daily light integral. And this is a very interesting concept that is related to light intensity very much. But instead of looking on how much light intensity there is at one moment, 1 second of time, so to say, the daily light integral is looking about the total amount of photons that hits a square meter per day. So you are essentially collecting all of the photons that fall on the surface over a day. This is similar to if you put a bucket out in the rain, and by the end of the day you take it in and you see how much water has accumulated in the bucket over the course of the day. That would be the analogy for the daily light integral, how much light has accumulated on the surface over the course of a day. And here we are measuring this in moles per square meter per day, essentially because it's a very large number. So it's not a micromole anymore, it's a mole. It's going to be a very large number of photons that has accumulated over the course of the day. This is very much of importance to anyone who's growing plants, to keep track of how much light do I get in total on my plants per day. And if you're indoor, calculating the daily light integral is pretty straightforward. We're not going to look at the formulas or anything like right now, but the only thing that determines how much light your plant gets is essentially how you use your lamp. So how much light output do you have in your grow room, and then you sort of say multiply by the number of hours that you have the lamp on. So it's pretty straightforward to calculate your daily light integral when you're indoors. But if you go instead to a greenhouse where you have both your lamp light but also the natural light from the sun, it gets much more complicated, because the natural light will vary over the day. And also it will vary over the year and so forth. And it will vary depending on where you are in the world. So if you are in Sweden, as I am, you have very long days in the summer, for example, and very short days in the winter. And you have very high intensities in the summer and very low intensities in the winter. So the location matters. I mean, if you are on the equator, you always have 12 hours of light, and you have very high light intensities in the middle of the day. All year around, so it's very different where you are. It's also important what type of greenhouse you have. So how much of the light do you actually lose in the greenhouse structure, both as reflection and also as shadows and so forth. And on top of that, you add your lamp use. So calculating your DLI in the greenhouse is a little bit more complicated. Yeah, it's something that perhaps it's a good thing to log that, use a sensor and measure over time, and you can capture all these variations and have that logged instead. But it's a concept, the daily light integral, the DLI, is a concept that is very central in horticulture, so it's something that you should keep track of.